Hey students, this is a video on section 2.2 of our elementary statistics book. 2.2 is our first section where we actually get to construct graphs. Okay? The type of graph that we're going to be learning how to construct is called a histogram. Okay? And a histogram is a special type of bar graph that we can use to display the data of a frequency distribution. So if you've already watched my videos and done your homework on frequency distributions, we're going to be using those tables that we made in order to construct these graphs. Okay? So obviously, the tables that we've already constructed, the frequency distribution, is useful for summarizing the data. A picture is worth 1,000 words. So just having a table doesn't cut it. Most people want to have a graph of some sort to display their data so that we are able to investigate the distribution or the shape of the data. Okay, so a picture is going to be much better. So a histogram, like I said, is a graph that is easier to interpret than just a frequency table or a frequency distribution. Okay, so what does a histogram look like? It looks just like a bar graph. It's just there are no gaps between the bars. So let me skip to a later slide. So we have these histograms here on this slide. This histogram on the left, as you can see, has vertical bars, and each bar has a height that represents the frequency of a certain class. And then these numbers on the bottom here, the 7, the 22, the 37, those are actually the class midpoints that we learned how to calculate in section 2.1. Okay, so the way they construct this type of graph, a histogram, is they make a frequency table, and then for each class, the height of each bar is the same as the frequency of that class. So for example, for this graph here, we can see that for the first class, the frequency is a little bit above 5. So we're going to say the frequency is 6. So that means in this first class, there were 6 people who had a commute time that was in there. Okay, and then the 7 here at the bottom, again, is the class midpoint. So the first class actually goes from 0 to 14, I think. This is actually the data that we did on the previous video from 2.1. Okay, and then also over here, we're going to talk about this more a little bit later. This is almost the same graph. In fact, it has the exact same shape as the graph on the left. But this graph on the right is called a relative frequency histogram. So for the height of each bar, instead of representing the frequency, the height of each bar is actually representing a relative frequency, which is a percentage. Okay? So just the same way we made a relative frequency table, we can also make a relative frequency histogram. But notice that the shape of that graph is going to be the same as the shape of our regular histogram. So this one on the left is a histogram, and then the one on the right is a relative frequency histogram. So that's what it looks like. So let's talk more about how we construct one. So going back, the formal definition of a histogram is a graph consisting of bars of equal width, as you noticed in the picture, probably. Each bar has the same width, and they're drawn adjacent to each other. Adjacent means there's no gaps between the bars. Okay, so really the only difference between a histogram and a regular bar graph is that there are no gaps in between the bars. So in particular, what we're talking about is a bar graph has gaps. So a bar graph would also have vertical bars, but the height of each bar wouldn't be representing a frequency in most cases. And with a bar graph, there are usually going to be gaps in between each bar. Okay, so a bar graph would look like this. Okay, so for a bar graph, it has gaps, has a gap between each bar. Okay, and another thing about bar graphs is they're usually representing, instead of the horizontal axis representing classes in a frequency table, the horizontal axis might represent categories. So the categories could, for example, be if our data was representing different types of fruits, just as an example, then our bar graph might be labeled with apples, oranges, and bananas. And this could be types of fruit that people prefer, but apples, oranges, and bananas aren't something that would be classes in a frequency table. So they would actually just be categories. So in general, bar graphs actually represent categorical data. Okay, so categorical data is what we do for a bar graph. And we're going to see more actual bar graphs in the next section. In section 2.3, we're going to see all kinds of graphs. But then in this section, we're focusing on histograms. So what do histograms look like? Well, we already saw a picture of one, but just real quick, I can sketch another one, just so that we can kind of see them side by side. So a histogram would actually have, it would look awfully similar to the bar graph, but you'll notice that there are no gaps in between the different bars. So I'm just making a histogram here. And those are supposed to be equal width. Obviously, I'm not that good at drawing, but those are supposed to be equal width. So for a bar graph and a histogram, each bar is equal width, but with a histogram, there are no gaps between the bars. The only time you would have a gap is if you didn't have any data values there. Now, a bar graph is going to be categories, like we said, like apples, oranges, bananas. That was our example. Whereas histogram is actually going to represent numbers from a frequency table. Or in the case of a relative frequency histogram, the height of each bar will be a percentage. So rather than being categorical or qualitative data, here we're dealing with, in a histogram, we're actually dealing with quantitative data. Okay? And remember, the word quantitative just means quantitative data would be numbers. All right. So for example, for our bar graph here, let me go ahead and label it. I just have to erase this real quick. For our bar graph, like I said, for our example, this first bar might represent the number of people who like apples, and then the next bar actually might represent the number of people who like oranges. Okay, let me write a little bit smaller here. So apples, oranges, and then the last one will be bananas. So the reason those are called categorical data is because their names are categories. Whereas with quantitative data, where you have a histogram, or a relative frequency histogram, as the case may be, rather than having categories as our horizontal axis, we're going to actually have numbers. So like we saw in the graph that we already looked at, usually people do the class midpoint in the middle of each bar. So this might be, say, 10, 20, 30, and 40. And so, for example, these could be representing numerical data that we've gathered, and the height of each bar represents a class. Okay? So hopefully you're able to see the difference between a bar graph, which is categorical data and usually has gaps between the bars, and a histogram, which is going to be quantitative data, so numbers rather than categories, and there are no gaps between the bars. Okay, and I didn't really say what these numbers represent, but they could represent anything, really, anything that you could measure. So it might be like ages of people. Okay, so this could be representing age of people in the study in years. But as long as it's numbers that actually count something or measure something, then that's when we use a histogram. And then, you know, for how high the bars are, the height of the bars usually represent the frequency. Okay, so let me write a little bit smaller here. So the height of each bar will represent a frequency in a histogram, whereas for a bar graph, it could represent frequency, or like here in this example, it would be the number of people who prefer a certain type of fruit. Okay, which is still a frequency, but it would be a frequency of a category rather than a frequency of a class. So you're mostly just looking at the horizontal axis. Okay, so let's go back to these slides. Let's continue through here. So we've seen what a histogram looks like, and we've seen the difference between a histogram and a bar graph. But in this section, we're only doing histograms. In 2.3, we will see bar graphs in more detail. So notice here on the slides, it says that the horizontal scale represents classes of quantitative data values. So as I was just saying, quantitative means that the horizontal axis has to represent numbers that have mathematical meaning. So those numbers are actually counting or measuring something. And the heights of the bars correspond to frequency values. So you might even just say that a histogram is a special type of bar graph, but it all depends on your definitions. So our book doesn't call it a bar graph, they call it a histogram. Okay, now why do we care about histograms? As I said before, a picture's worth 1,000 words. It's obviously very helpful to have a picture that represents the shape of our data. So that shape is called the distribution of the data. So what's the shape of the data? Well, you can draw a curve that follows the histogram, and that will show you how it's spread out. So for example, on this later slide, this one here, we're able to see that we can even draw a curve here that sort of roughly follows the shape of this histogram. And that curve that you see there is actually a bell curve. That's going to be a normal distribution, which we're going to talk about in a bit. Anyway, what else is useful about a histogram? Well, it shows the location of the center of the data. So the center has different definitions. So you could think of the center as being the middle, roughly where the middle of the graph is. So for example, with a histogram like these, you might say that the center is somewhere over here to the left. And the center would usually be roughly where the maximum is, or the highest point of your graph. That's usually what people think of as the center. So because here the maximum is way over on the left side, we say the tail on the right here is longer than the tail on the left. Okay, but the center doesn't have to be on the left side. It can be in the middle. Like in this graph here, the green graph, the center is roughly in the middle of the graph. With this red graph over here, we can see that it's hard to identify a center because all of the bars are roughly the same height. So I guess with this one you could say the center is in the middle, but it's a lot more difficult to figure out where the center is just by looking at the graph. Okay, and then this graph down here on the bottom left, we have the blue graph. We can see that the center is really over on the left side. So from the center, the tail on the left, which is this part, is actually smaller than the tail on the right. And because the tail on the right is larger, we call this one skewed to the right. Okay. All right, but we'll talk more about that in just a second. So I wanted to finish this slide. So a histogram, or any picture really, any graph, will help display the shape of the distribution of the data, which is obviously very helpful for scientists to figure out what's going on when they're running a statistical study. Shows the location of the center, good to know, just by looking at the picture. Shows the spread of the data. So is all the data close to the middle, or is it all spread out? Or is it in two clumps, or three clumps? The data can be spread in a number of ways. And a picture helps represent the spread of the data. Okay, and then the last important use of a histogram is it identifies outliers. Now, we're not going to talk about this in much detail, but I want to at least introduce outliers. Outliers are just data values that are far away from the others. Okay? So the word outliers just means data values that are far away from all the other data values. Okay? Data values that are far away from the others. Okay, so the term outlier really just means it's an unusual data value. You've got all your other data values, but then all of a sudden you have this other data value that's way in some other position. So for example, what would that look like on a histogram? Well, we won't get to see it in this homework, but in a later homework, we'll see histograms or graphs that have outliers. But if you had a histogram, you might see something. If your histogram has this shape, and then it might have a gap where it has nothing, and then all of a sudden you might see something like this. So a bar all by itself over here. So these bars to the left would be considered normal values. Well, normal isn't the best word, but they're considered usual, not unusual. Whereas this one over here, this value or a couple of values that are way over here, these would be considered outliers because they're far away from these other values. Okay, so if you do have outliers, in other words, you have data values that are far away from the others, that has statistical significance. We talked about statistical significance in chapter 1. That means it has mathematical meaning. And we'll come back to outliers later on in the course. They're going to end up being a lot more important. But for now, I just wanted to introduce the idea of an outlier. Okay? All right, so let's go on to the next slide. Okay. So we've already looked at this slide, but I want to talk just a little bit more about it while I erase this board. So a relative frequency histogram is still just a histogram, okay? Has the same shape and horizontal scale as a histogram, but the vertical scale is marked with relative frequencies instead of actual frequencies, okay? So the only difference between a histogram and a relative frequency histogram, well, the histogram is on the left, and you'll notice that the vertical axis of this histogram represents frequency. The one on the right here is a relative frequency histogram, and you'll just notice that even though it has the exact same shape as the graph on the left, the only difference is with this vertical axis here, we can see that the vertical axis is actually representing relative frequencies rather than frequencies. That's the only difference. So we just have percentages. And remember in section 2.1, I showed you guys how to calculate relative frequencies. So relative frequency is calculated from a frequency by just using the formula F over N. So you can watch my videos from 2.1 for details on calculating relative frequencies. Okay, but what's interesting is really just that they have the exact same shape. But that should kind of make sense because even though we're converting a frequency into a percentage, the number of values in each class is not changing. So each frequency is not changing. So if you convert it to a percentage, it's still going to have the same shape. We still have most of the values in the second class and third class, okay? And changing it to a percentage does not change the shape of the histogram. Okay, now this slide's a little bit less important, but I left it in here just in case you were interested in this. So this slide is about critical thinking interpreting histograms. So we explore the data by analyzing the histogram to see what can be learned about the data. And this here is called an acronym, CVDOT, or CV-DOT. We aren't going to be using this much, so I'm going to go through this slide pretty quickly. But as we're already talking about, the importance of histograms, or any graph really, is to represent the center of the data in a picture so we can see it, the variation or the spread of the data, that's the V, the shape of the distribution, so that would be the shape of our graph, whether there are any outliers. So remember, outliers are data values that are far away from the other values. And then the last one is time. So time means your histogram can actually change over time, so you'll have different histograms. Okay, but time's probably the least useful one here. So it's mostly about the C, V, D, and the O. But this doesn't show up on your homework, so we're going to go ahead and go on to the next slide. But I just left it here in case you're interested in critical thinking. Okay, so let's go back to this. So these are common distribution shapes. These are all histograms, by the way. It's just you'll notice that for the top left, and bottom right, they have a lot more bars. So the bars are a lot narrower, and there are a lot more of them. With the red graph over here on the top right, for this red graph, we'll notice that there are fewer bars. But these are all still histograms. So a histogram can have a lot of different classes, like these ones, or it can have fewer classes, like the red one, or even fewer, like the ones that we have done, such as this one. This one has only 1, 2, 3, 4, 5, 6, 7 classes. So there are only 7 bars. Okay, but what we're really concerned about here in this slide is learning some very common shapes. And you're going to need these for your homework. So the common distribution shapes, remember distribution is sort of synonymous or means the same thing as the word shape. Well, what's the shape of this one? This one here, the top left, is roughly bell-shaped. And a bell-shaped curve where the center is roughly in the middle of the graph, where the left side is roughly symmetric with the right side, is called a normal distribution. Okay, so a normal distribution, because this histogram is roughly bell-shaped, this is another one here, by the way, that's roughly bell-shaped, we say that the data have a normal distribution. But in order to be normal, it has to be roughly bell-shaped. And then another important detail besides being roughly bell-shaped is the left half of the graph has to roughly be a mirror image of the right half. So even though it's not on this slide, it has to be roughly bell-shaped and also symmetric. Okay. And the word symmetric, if you haven't heard it before, the word symmetric basically just means the left half is a mirror image of the right half. Okay, so we can see that in this graph. So we can see that the center is, right about here, at, roughly where the highest point of the graph is. And we can see that even though it's not perfectly symmetric, I mean, looking at the bars, the left half isn't a true mirror image of the right half. We can still roughly see that on the left half, this shape is still almost the same as the right half. And the easiest way to see it, of course, is to look at this curve that they've drawn here over the histogram. So that is called a bell-shaped curve, that shape there. And it's called a normal distribution because it's actually the most common type of distribution that you find in the real world. So if you randomly gather enough data, many things in the real world, as long as you have at least 30 or more data values, it will very often have a normal curve or a normal distribution. Okay, but again, symmetric means the left half has to be roughly a mirror image of the right half. All right, well, what about this red graph here? What about this red graph? Obviously, we can see that on the top left, we have a, this one is clearly bell-shaped. So, and the center is right in the middle, and the left half is roughly a mirror image of the right half. So clearly this one is normal. Well, what do we call this graph on the top right? This is called a uniform distribution. This graph is less common, but it does show up quite a bit in the real world. So you'll notice here that for a uniform distribution, every bar is roughly the same height. Okay, so this one we don't actually have any slides on, but I do want to talk about it. So for uniform, every bar is roughly the same height. So let me write that somewhere where you can actually read it. So each bar is roughly the same height. So obviously in the real world, it's not going to be a perfect rectangle, but if you kind of squint at it, you can see that this has a rectangular shape. So a normal distribution is roughly a bell shape. So this one right here is a bell shape, roughly bell shaped, because it's shaped like a bell. But for a uniform distribution, the red graph, it has more of a rectangular shape. And an example of a uniform distribution from the real world would actually be lottery numbers. So if you had lotto numbers, and for some reason you only had the numbers 0 through 9, I don't know what kind of lottery would only have the numbers 0 through 9. But let's just say for the sake of argument for this graph, we had a lottery where each possible number was equally likely, and the only numbers in this lottery would be 0 through 9. So each ball would be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Then that would have a uniform distribution. And it's basically just saying each number is roughly equally likely, and that's why each bar is roughly the same height. Okay? All right, so that is bell-shaped normal distribution. Top left, uniform distribution, rectangular shape, top right. So then what about the bottom left and the bottom right? You'll notice that for both of those graphs, for the bottom left and the bottom right, you'll notice that the center of the two bottom graphs isn't in the middle of the picture. Okay, so it's not in the middle of the graph. And when I say center, I mean really you're looking at the maximum or the highest point of the graph is what we consider to be roughly the center of the graph when we're looking at it. Now later on in statistics, we're going to be calculating things like the mean, the median, the mode, and that's a different, that's a more mathematical definition of the word center. But looking at this graph on the bottom left, we can see that the center is way over on the left rather than in the middle like the green graph. And then for this graph on the bottom right, we can see that the center is over on the right side. So these are both called skewed graphs, and that's what we're going to talk about on the next couple of slides. So the one on the left is called skewed to the right, and the one on the right is called skewed to the left. So let's take a look at what that means. So when you have a skewed graph, skewness means that a distribution of data is skewed if it is not symmetric and extends more to one side than to the other. So remember, with a normal distribution, we said that it had to be bell-shaped and also roughly symmetric. So the left half and the right half had to roughly be a mirror image of one another. So if the graph extends more to one side than to the other, then we can see that for example, here on this graph, it's all zoomed in now, we can see it better. This one is called skewed to the right or positively skewed because the tail on the right is longer than the tail on the left. So how do we find the tail on the right? Well, we just look at the graph and we look for the highest point on the graph, which is, around here. So that's like the middle or the center of. Center is a little tricky because center is something that you can actually calculate. But I could at least call this the middle or the highest point. You can also just call it the maximum. So this right here would be our maximum. I'm still getting used to writing on this board. I need to write smaller. Okay, so here's our maximum. But the reason we call it skewed to the right is we can see the tail on the right. In other words, how far it is from the maximum to the right side of the graph is actually longer than the tail on the left. The tail on the left is how far it is from the maximum to the left side. Okay, so sorry, I am having trouble writing this low, so a little technical difficulty here, but also that's not lined up. Okay, anyway, so this distance right here is called the tail on the left. And then this distance over here from the maximum to the right side is the tail on the right. So for the tail on the left, we can see that that is shorter than the tail on the right. So we say it's skewed to the right. And if you could understand all of that, then you'll find the next slide to be very easy, because skewed to the left means the exact same thing. It's just the tail on the left is instead going to be larger than the tail on the right. So let's go to see the next slide, which is skewed to the left. So with this graph, we can see that this is not symmetric once again. And if we look at the maximum, it's way over on the right side. So here's our maximum. And this is way over on the right side of our graph. And you know what? Let me write it up here. The tail on the left here is going to be from here on the left side all the way to the maximum. And then the tail on the right is going to be the distance from the maximum over to the right side of our graph. Wow, it's a lot easier to write this high on the board. It was difficult for me to write this low on the board, so that's why it was harder for me to draw that. Okay, so we got our max, and then the distance from the max to the left side of the graph is called the tail on the left. Okay. And then the distance from the max to the right side is called the tail on the right. Okay, so this one from here to here is the tail on the right. Okay, and what's important to realize here is even though I was calling it the center earlier, there are a lot of different names for what we consider to be the middle of the graph. I probably shouldn't have used the word center, so let's stick with the word max from now on. But some people would call the center of the graph, when they're looking at the picture, basically where the middle of the graph is, which is the highest point or the maximum. Okay. But what you're going to notice here, and what I want to kind of summarize, is that this is not on the slides, but I wanted to just write it on the screen here. If your tail is longer on one side, then we're going to be skewed on that side. So many of you probably have already figured that out from what I was describing. Okay. So to summarize, skewed left means we have a longer left tail. Okay? And then skewed right, of course, means we have a longer right tail. Longer right tail. right, and that's really all there is to it for skewed graphs. All right, so that takes care of this video. And then when you're doing your homework, I just wanted to talk briefly about how to do your homework. So with your homework, they will be giving you frequency tables. And then rather than having you construct a histogram from scratch, it'll be multiple choice. So they'll have 4 histograms, and only one of them will be correct. So it's really not too bad. All you have to do is look at the frequency table and look at the height of each bar in your histogram and read what the height of each bar is. And as long as the height of each bar is the same as the frequencies in the frequency table, then that means you have the correct graph. So you have the correct histogram. Okay? And then the slides take care of pretty much everything else. So I think you'll be good. So thank you for watching, and I will see you next time.